Integrated Operations Planning. Supply chain planning. A supply chain planning system and support information systems seeks to integrate information and coordinate over logistics and supply chain decisions while reorganizing the dynamics between other form functions and processes. The three drivers of effective planning are supply chain visibility, simultaneous resource consideration, and resource utilization. Supply chain visibility. The first driver of planning system development is the need for visibility regarding location and status of supply chain inventory and resources. Visibility implies not only being able to track supply chain inventory and resources, but also that information regarding available resources can be effectively evaluated and managed. Simultaneous resource consideration. A second planning system requirement is the need to simultaneously consider supply chain human capacity, material requirements, and constraints. Supply chain design must consider customer demand for product quantity, delivery timing, and location. While some of these customer requirements may be negotiable, logistics must excuse to the agreed to requirements and standards. Resource utilization. Logistics and supply chain management decisions influence many enterprise resources, including production and distribution facilities and equipment transportation and inventories. With functional resource trade-offs in mind, the final driver of planning system development is the need for a coordinated approach that considers service requirements while minimizing combined supply chain resources. This is a physical capability when supply chain and firm performance place a strong emphasis on overall asset utilization. Supply chain planning applications. Supply chain is increasing in frequency and scope. There are some applications common for most supply chain environments. These include demand planning, production planning, and logistics planning. Demand planning. Demand management develops the forecast that drives an anticipatory supply chain processes. The forecasts are the projections of monthly, weekly, or daily demand that determine production and inventory requirements. Another aspect of the demand management process focuses on creating forecast consistency across multiple products and warehouse facilities. Lastly, the demand management system rationalizes the detailed logistic plans, unique forecasts for each warehouse and product to the aggregate product group and national plans. Production planning. Production planning uses the statement of requirements obtained from demand management in conjunction with manufacturing resources and constraints to develop a workable manufacturing plan. The objective is to satisfy the necessary requirements of the minimum total production cost while not violating any constraints. Logistics planning. Logistics planning coordinates transportation, warehousing, and inventory within the firm and between supply chain partners. Logistics planning integrates overall movement command vehicle availability and relevant movement cost into a common decision support system that seeks to minimize overall freight expense. Inventory deployment. Inventory deployment represents one of the major enterprise integration of sales, marketing, and financial goals. The inventory deployment activity can be completed independently by individual supply chain function in an integrated manner by supply chain overall, or in a coordinated manner by the entire firm. The key objective in an inventory deployment system is an integrated inventory plan to what is increasingly being termed an APS system. Sales and Operations Planning, or S&OP. S&OP is a process that coordinates demand and supply plans across the organization. The process includes information sharing and accountability to systematically develop a common and consistent plan. In general, the S&OP technology integrates the firm's information regarding forecast inventory availability, production resources, and other resource constraints. S&OP process. An integrated S&OP process is increasingly necessary for effective supply chain operations. The S&OP process collaboratively establishes a coordinated plan for responding to customer requirements within the resource constraints of the enterprise. Traditionally, firms have sequentially and often independently developed financial, sales, and operations plans. First, finance develops revenue plans often designed to meet the expectations of Wall Street. Second, sales develop marketing plans and tactics that meet the revenue targets for the firm's product groups. This includes establishing specific product innovation pricing and promotion plans to achieve the desired results. Finally, supply chain operations development materials, manufacturing, and logistics plans that can meet customer demands or the operating constraints of the firm and its supply chain partners. Making S&OP work. Positioning S&OP as a core business planning process requires a well-understood operational framework. Successful S&OP requires collaborative analysis of available information, shared operational metrics, and senior leadership. The keys to successful S&OP implementation are presented in the table. APS System Overview. To correspond with the planning and execution of effective logistics and supply chain strategies, supply chain planning systems incorporated both spatial and temporal considerations. The spatial considerations include movement between raw material providers, manufacturing plants, warehouses, distributors, retailers, and the end customer. The temporal considerations include movement timing and scheduling. The APS system is a network including plants, warehouses, and customers as well as transportation flows. This network reflects the resource status and allocation at a point in time. Supply chain planning tools like APS offer the ability to thoroughly evaluate complex trade-offs involving a large number of alternatives. APS system components. While there are many conceptual approaches to designing supply chain planning applications like APS, the major components are fundamentally the same: demand management, resource optimization, and resource allocation. Demand management. The demand management module developed the requirement projections for the planning horizon. In effect, it generates sale forecasts based on sales history, currently scheduled orders, scheduled marketing activities, and customer information. Resource management. The resource management component designs and coordinates supply chain system resources and constraints. Since APS systems use the resource and constraint information to evaluate the trade-offs associated with supply chain decisions, information accuracy and integrity are critical to provide optimal decisions and enhance planning system credibility. Resource optimization. The resource optimization module is the computational engine or black box of the supply chain planning system. The resource optimization module can also be used to conduct sensitivity or what-if analysis to determine the impact of changes in market requirements or constraints. Supply chain planning benefits. While supply chain planning system benefits were discussed earlier, there are three broad benefits that accrue from planning system utilization. These are responsiveness to changes, comprehensive perspective, and resource utilization. First, logistics and supply chain managers have used extended lead times and schedule freezes to plan for future supply chain activity. Today's customers requires more responsiveness to market needs, and demand for lower inventory levels rules out long cycle times. Second, effective supply chain management requires planning and coordination across functions and between supply chain partners. The process must consider the trade-offs associated with shifting activities and resources across functions and organizations. Such a comprehensive perspective increases planning process complexity substantially. Third, another major planning system benefit is enhanced resource utilization. More effective and responsive planning allows a more level assignment of resources for existing sourcing, production storage, and transportation capacity. Supply chain planning considerations. Prior to the actual implementation, there are many considerations for supply chain planning system adoption. Managers cite their major considerations to be integrated versus bolt-on application, data integrity, and application education. The first consideration concerns the level of integration with other supply chain applications. Technically, there are three options for acquiring and implementing planning applications. The first is development using internal firm resources. Options 2 and 3 are to use a supply chain planning application that is integrated within the firm's ERP system, or one from a third party that bolts onto the firm's ERP system. The alternative is to use a bolt-on or best-of-breed approach that seeks to identify the best supply chain planning system to the firm on the basis of features and functionality and then attach it to the firm's ERP system. Data integrity is a second major consideration for supply chain planning system implementation. Planning systems rely on absolute data integrity for effective decision making. While data integrity has always been important, it is more critical for planning systems since missing and inaccurate data can dramatically impact decision reliability and stability. A strong focus on developing and maintaining data integrity is critical to effective planning system implementation. Education regarding planning system application is the third major consideration. Although knowledge can be initiated through training, it must be refined and extended to education and experience. Integrated business planning. S&OP is evolving into Integrated Business Planning or IBP in many organizations. Given the name, the implication for S&OP is that it is limited to sales and operations. While IBP is similar in concept to S&OP, it is designed to include greater financial integration, increased inclusion of strategic initiatives and activities, improved simulation and modeling of alternatives, and easier translation between aggregate and detailed levels of planning. Supply Chain Planning Summary. The major objective of an integrated supply chain planning capability is coordinated capacity management of relevant supply chain resources, including manufacturing plants, distribution centers, and transportation resources. Collaborative Planning, Forecasting, and Replenishment, or CPFR, is a process initiated by the consumer products industry to achieve such coordination. It does not replace replenishment strategies but supplements them by a cooperative practice. In essence, CPFR coordinate the requirements planning process between supply chain partners for demand creation and demand fulfillment activities. Forecasting. Accommodating customer requirements in most supply chain arrangements requires a forecast to drive the process. The forecast is a specific definition of what is projected to be sold, when, and where. The forecast identifies requirements for which the supply chain must schedule inventory and operational resources. Forecasting requirements. Although consumer demands in terms of service level and product variations are increasing, the focus on reduced supply chain assets simultaneously requires more timely and accurate forecasts. Logistics forecasts are necessary to support collaborative planning, to drive requirements planning, and to improve resource management. Collaborative planning. A collaborative forecast, jointly agreed to by supply chain partners, provides a common goal that can be basis for developing effective operating plans. Without collaboration, each partner tries to plan the level and timing of demand for its customers both individually and collectively. Requirements planning. Once a collaborative forecast is developed, logisticians use the forecast to drive requirements planning. The plan determines inventory projections and resulting replenishment or production requirements for the planning horizon. Ideally, the requirements planning process operates collaboratively and interactively both internally across the firm's operations and externally with supply chain partners to develop a common and consistent plan for each time period, location, and item. Resource management. Once the plan is completed, it can be used to manage critical supply chain processes such as production, inventory, and transportation. Accurate forecasts collaboratively developed by supply chain partners along with a consistent definition of supply chain resources and constraints enable effective evaluation of trade-offs associated with supply chain decisions. Forecasting components. The forecast is generally a monthly or weekly figure for each stock-keeping unit and distribution location. The forecast components include base demand, seasonal, trend, cyclic, promotion, and irregular. Base demand. The base demand represents the long-term average demand after the remaining components have been removed. The base demand is the average over an extended time. The base demand is the forecast for items having no seasonality, trend, cyclic, or promotional components. Seasonal component. A seasonal component is an annual recurring upward and downward movement in demand. It should be noted that seasonality refers to consumer retail seasonality. Trend component. A trend component is the long-range shift in periodic sales. Trend may be positive, negative, or neutral in direction. Cyclic component. A cyclic component is characterized by periodic shifts in demand lasting more than a year. Cycles may be either upward or downward. Promotional component. The promotional component characterizes demand swings initiated by a firm's marketing activities such as advertising, deals, or promotions. Irregular component. The irregular component includes the random or unpredictable quantities that do not fit within the other categories. Because of its random nature, this component is impossible to predict. Forecasting process. Supply chain operational forecasts are normally developed for daily, weekly, or monthly periods. An effective forecast management process requires a number of components. process foundation is the forecast database, including open orders, demand history, and the tactics used to simulate demand that has promotions, special deals, and products changes. The development of an effective forecast requires a process that integrates three components: forecast technique, forecast support system, and forecast administration. Technique. A technique component is a mathematical or statistical computation used to combine base, seasonal, and cyclical components with elements of promotion history into a forecast quantity. Techniques include the time series modeling, in which sales history is a major factor, and correlation modeling, in which relationships with other independent variables are the major forecast drivers. Support system. The forecast support system includes the supply chain intelligence to gather and analyze data developed in the forecast and communicate the forecast to relevant personnel and planning systems. This component allows consideration of external factors such as impact of promotions, strikes, price changes, product line changes, competitive activity, and economic conditions. Administration. Forecast administration includes the organizational, procedural, motivational, and personal aspects of forecasting and its integration into the other firm functions. The organizational aspect concerns individual roles and responsibilities. It is important these roles and responsibilities be specified in detail when defining the forecast administration function. Effective administration requires that organizational responsibilities and procedural guidelines are documented and measured. It also requires that forecast analysts be trained in both the process and the input of forecast and supply chain logistics operations. Forecasting techniques. Demand forecasting requires the selection of appropriate mathematical or statistical techniques to generate periodic forecasts. The effective use of a technique requires matching the characteristic of the situation with the abilities of the technique. Some criteria for evaluating the applicability of a technique include accuracy, forecast time horizon, the value of forecasting, data availability, type of data pattern, and experience of the forecaster. There are three categories of forecast techniques: qualitative, time series, and causal. Qualitative. Qualitative techniques rely heavily on expertise and are quite costly and time-consuming. Qualitative forecasts are developed by using surveys, panels, and consensus meetings. Time series. Time series techniques are statistical methods utilized when historical sales data containing relatively clear and stable relationships and trends are available. Time series techniques include a variety of methods that analyze the pattern and movement of historical data to establish recurring characteristics. Four time series techniques in order of increasing complexity are moving averages, exponential smoothing, extended smoothing, and adaptive smoothing. Moving average forecasting. Moving average forecasting uses an average of the most recent period. See, the average may use any number of figures time. Although moving averages are easy to calculate, there are several limitations. Most significantly, they are unresponsive or sluggish to change, and a great amount of historical data must be maintained and updated to calculate forecasts. Exponential smoothing. Exponential smoothing bases the estimate of future sales on a weighted average of the previous demand and forecast levels. The prime advantage of exponential smoothing is that it permits a rapid calculation of a new forecast without substantial historical records and updating. Extended exponential smoothing. The extended exponential smoothing incorporates the influence of trend and seasonality when specific values for these components can be identified. Like basic exponential smoothing, extended smoothing allows rapid calculation of new forecasts within minimal data. Adaptive smoothing. Adaptive smoothing provides a regular review of alpha factor fit. More sophisticated forms of adaptive smoothing include an automatic tracking signal to monitor error. When the signal is stripped because of excessive error, the constant is automatically increased to make the forecast more responsive to smoothing recent periods. Causal. Causal or aggression forecasting works well when a leading variable such as price can be identified. However, such situations are not particularly common for supply chain applications. Regression forecasts use the correlation between a leading or predictable event and the dependent demand SKU sale. Forecasting accuracy. Forecast accuracy refers to the difference between forecast and corresponding actual sales. Forecast accuracy improvement requires error measurement and analysis. Another consideration is the measurement level or aggregation.